Let's talk about the dot product in section 9.3. The astute observers have realized that we have this new set of things to work with called vectors, and we've defined addition and subtraction and a form of multiplication, but it wasn't a multiplication between two vectors. It was a multiplication of a scalar or a number times a vector. Well, we're actually going to have a couple of different ways we can multiply two vectors. One of them is going to be the dot product, but we get to it in a little bit of a roundabout way. We get to it through the idea of work. Now, as you may know from your science classes, physics classes, that work is simply defined as a force that it takes to move something times the distance that it moves. So work is force times distance in general terms. So a very simple example we can look at is, suppose we have some box and we're going to move that box with a force of 10 newtons. Newtons being a unit of force, and we're going to say it moves it for 10 meters. And we're just going to move it in a straight line here, so we would have some straight plank here that we're going to move it, and let's suppose here is our box, and we're going to have that force pulling in this direction. And notice that that force is represented by a vector, so the direction and the magnitude are represented graphically here. This is our force vector. It is given by 10 newtons, and so if we were going to be drawing this and wanted to be precise, we would make this length 10 units, whatever the unit happens to be that we're drawing with here. And let's suppose then that we are going a distance, as we said, of 10 meters. So the box will end up right here at the end of this plank. Well, it's pretty easy to figure out what the work's going to be. The work is going to be equal to the force, which is 10 newtons, times the distance, which is 10 meters. 10 times 10, let me get my calculator out here. Alright, that's 100 Newton meters, or as we usually refer to Newton meters, as joules. So 100 joules of work is required if we use a force of 10 newtons to move an object 10 meters. Now, of course, things don't always work out so nicely. A lot of times we may be pulling at an angle or moving things at an angle. So let's consider another situation. Let's suppose we have a force this time of 20 newtons, so twice the force now, and it's going to move an object the same distance. We'll say the same distance of 10 meters, but we're going to say that the force is pulling at an angle of 60 degrees with the horizontal. Okay, so again, a picture is beneficial here. Here is our plank that we're going to be pulling our object across. Here is our object itself. Our force now is going to be pulling in that direction, but pulling at an angle of 60 degrees with the horizontal. So roughly about there. This is 60 degrees right here. Okay, again, the length, this should be a longer vector than what we represented originally because it has twice the magnitude, twice the amount of pull. The direction is different and the magnitude is different. But this is our force vector F. And I look at this, and this isn't exactly right. This is our force vector. It's 10 newtons. Let me just amend this a little bit just to try and be precise. Our force vector is represented by this. The length of that vector is 10. So we would say, using our notation for the length of a vector, the absolute value signs, the length of that vector is 10, and so that the force is representing a force of 10 newtons. Here, the length of this vector would be 20 units, and so we're representing a force of 20 newtons. Well, again, work is going to be equal to force times distance. Again, we're going to be pulling this for 10 meters across this plank here. But we have to think about, are all 20 newtons of that force vector going towards pulling that object? Well, no, of course not. But there is going to be a certain portion of that force vector that's going towards pulling that object. What portion is that going to be? Well, we'll form a triangle here. So let's go ahead and start at this point where it's attached to the object. We're going to form a right triangle. We got good old Pythagoras that'll help us out here. You can see that this horizontal portion, I'll represent that as A. I'll represent the vertical portion as B. The horizontal portion of this force vector, that's what's actually doing the work in pulling that object. So, what is A? Well, We can figure that out pretty easily. So our force vector, again, we can represent in that component form as A times I plus B times J, where A is the contributing part of F, the part that is actually contributing to the work that's being done. Let me say what I wanted to say. Contributing part of F that we're concerned about. Well, how are we going to figure that out? Again, we know that the length of this vector here is 20, so we have a triangle with a hypotenuse of length 20. We know the angle here, so a little bit of trigonometry will help us figure that out. We know that the cosine of 60 degrees is going to be equal to the adjacent side of A divided by the length of the hypotenuse, which is 20. And so A is 20 times the cosine of 60 degrees. Of course, the cosine of 60, as you know, I hope you know and should know, is a half. And so we get 10 newtons that are actually contributing to the work. And so we can see then that our work is going to be those 10 newtons times the 10 meters the object is being pulled. We get the same amount of work done, 100 Newton meters, or 100 joules. Okay, so it's a lot here, but let's kind of generalize this and get our concept of the dot product based on this definition of work. So let's again take a look at a more general situation here. Let's take some object that we're going to pull for a certain distance, and I'm going to represent that distance as a vector here. I'm going to call this D, where D is what we call our displacement vector. So D is our displacement vector. So it represents the direction my object is going to move and how far it is going to move. So the magnitude of D is the distance. And we're going to have some force vector F pulling at some angle, say like this. So F, of course, is our force vector. All right, and that's going to form a certain angle. Here we'll call that theta. Now, what portion of F contributes to the work being done in moving this object? How do we find what our work is? Well, remember, it's going to be this portion of the force vector, this horizontal component of the force vector, and we found that, again, if we call that A was equal to the magnitude of F times the cosine of that angle theta. And so our work, which is force times distance, well, our force is going to be that horizontal component of the force vector. That's the magnitude of F times the cosine of theta times the distance, which is the magnitude of our displacement vector. And we're usually going to write this as the magnitude of F times the magnitude of D times the cosine of the angle between them. And now we will define the dot product of two vectors. And there's our notation. So F dot D. This is a very specific notation. A lot of times we just use a dot to show multiplication between two numbers, but now dot means something specific, a specific way to multiply two vectors. It means we take the magnitude of one vector times the magnitude of the other times the cosine of the angle that is formed if you start them at the same place. Okay? Now, clearly your theta here has to be less than 90 in order to have the work being done. If I pull the object this way and I want to move it this way along D, well, that doesn't make any sense. In fact, what would we have then? We could think of being a negative amount of work, because we'd actually be pulling the object in the opposite direction we want it to go. And so you can see then that if we do have a theta that is bigger than pi over 2, well, what's true about the cosine of that theta? Yeah, it's going to be negative, right? Cosine is going to be negative, and in that case, the work definition really makes no sense. We can still use it in our dot product definition, but we will have a negative dot product if the angle between the two vectors that we're dotting is bigger than pi over 2. Okay? So, in general, if we have given two vectors, and I will call them, say, u and v, we define the dot product to be u dot v, and it's the magnitude of u times the magnitude of v times the cosine of the angle theta between them. The smaller of the two angles. I mean, you could make a case that here's my angle theta, but we're never going to do that. We will always take the smaller, so that's out. We're going to take the smaller of the two angles between the two vectors, the one that is less than pi, less than 180 degrees. Okay? Of course, if it's equal to 180 degrees, you got a different situation here, right? Let's take a look at our different situations. Suppose I've got a vector u here and a vector v here, and let's think about there's theta. So again, we will always take theta to be between 0 and pi. Okay? Now, as we had said earlier, if theta is acute, so less than pi over 2, greater than or equal to 0, less than pi over 2, then we can see that u dot v, magnitude of u, magnitude of v, cosine of theta, will be positive, right? Because magnitude is always positive. You're taking the square root of numbers squared, and the cosine of an acute angle is positive. So we'll have a positive dot product. If, however, as we mentioned earlier, theta is obtuse, and we will say less than or equal to pi, then not a dot b, it's our vectors u and v here, u dot v will be negative, precisely because, again, the magnitude of u is positive, magnitude of v is positive, but the cosine of the angle will be negative, so the dot product will be negative. Doesn't make sense in the context of work, but it does make sense in how we're defining the dot product. We can have a negative dot product. All right. Now, if theta is equal to pi over 2, then, keep wanting to write a for some reason, u dot v, well, is going to equal 0, right? Because the cosine of pi over 2 is 0. So the dot product will be equal to 0. And that certainly makes sense. I mean, if we go back to our work example, if I were to, say, pull straight up on this, well, I'm not going in the direction I want to go, but I'm not going in the opposite direction. I'm essentially doing nothing, advancing the cause of moving this object the way I want to go. So we say the work done would be 0. So it kind of makes sense in the work definition. All right, but that's always going to be the case. If I have two vectors that form an angle of 90 degrees or pi over 2, then the work done is going to be 0. In other words, the dot product of those two vectors is going to be 0. This is a very, very important thing. So important, I'm even going to change colors here. Here's what we're going to say. If, well, actually, I'm not going to start it that way. It's going to be an if and only if statement. We'll say two vectors, and we'll call them u and v, are going to be referred to as, well, we'll refer to them as orthogonal. It's a little bit more general of a term, but whenever you hear the word orthogonal, you can think of perpendicular. Okay, it just means they meet at a 90-degree angle, orthogonal or perpendicular, if and only if their dot product is 0. Notice I'm not putting a vector sign over the 0. This is the number 0, not the vector 0. And that's a very important thing. The dot product takes two vectors and gives us a number or a scalar. All right, something very important to remember. All right, in fact, I'm going to write that down. In red. I mean, that means it's important, right? If it's in red. That's why we grade homework papers in red. We take two vectors, we get a scalar when we do the dot product. We don't get another vector. Actually, the real reason we do it in red is because it destroys self-esteem, and that's what we're shooting for. That's just a little joke there.